Dear students, welcome to another lecture of mathematical methods in physics. We are learning complex numbers and their functions. So we will do another example in the start, and then we proceed to other concepts. So you may be asked to evaluate some complex function, for example, like this: one one plus iota squared divided by 1 minus iota, and you are asked to determine which complex number is that. Determine which complex number is this on a Cartesian plane or complex plane, simple complex plane. So that would be easy and difficult also. So if you are asked to do everything in Cartesian geometry, you have to evaluate it in a proper way. First, I will tell you an easier way to evaluate everything, but that does not include any understanding of the subject. So, for example, you can do this problem by just simply evaluating this equation. So, 1 plus iota squared divided by 1 minus iota, and you just multiply and divide it with 1 plus iota, and then it becomes easy that on the top you have 1 plus iota cubed, and at the bottom you have 1 plus 1. So that is, you use the formula a plus b into a minus b equals a squared minus b squared. So this can be that simple in some cases, and when you simplify this thing, you will get, at the end of the day, you will get minus 1 plus iota. In a couple of steps, you get minus 1 plus iota, and this is the final result you are looking for. But you have done some calculation, but you don't know what you have done, and you don't have any understanding of the problem as such in terms of complex numbers. So what we are going to do now, we will evaluate this thing in a more like a descriptive way, and we will calculate each complex number in this fraction. So we have now 1 plus iota squared on top and 1 minus iota at the bottom, and we evaluate these two complex numbers. We treat them as two different complex numbers, and we see how they look like and what is their meaning, and then we just combine them. That we will do kind of visually or on a complex plan. So let's take the first complex number, that is 1 plus iota squared, and we just take its portion that is inside the square. So initially we take this one, and that is basically 1 plus iota squared. So let's see what is 1 plus iota. So if you equate it with the x plus iota y, you see that in this case x is 1, y is 1. So that means this complex number is in the first quadrant. It is in the first quadrant because both x and y are positive. Let's determine r. Now we want to express this in the form of r e to the power iota theta form. So what is r then? R is simply x square plus y square whole square root. So that would be square root of. What is theta? Theta you determine by taking tan inverse of y over x, that is 1 over 1, and that you know already, we have done this problem before. So that is, the theta is now pi over 4. This is very simple until now. And what you do, you just take this 1 plus iota squared and insert the values r e to the power iota theta. Theta is now pi by 4, and now you square it because you have square in the original formula. And what you get 2 exponential raised to the power iota. That power comes inside, and that becomes iota pi over. So that is your the upper portion of the complex number that you are evaluating using some understanding of complex numbers. And next we do evaluate is the lower portion of the complex number. The lower portion is 1 minus iota. And as I told you that if there is a complex number x plus iota y, its complex conjugate is the number with this iota sign change, x minus iota y. So in principle, this 1 plus iota y, 1 minus iota is a complex conjugate of 1 plus iota, and it should be like that, that if we had our x 1 plus, this is our 1 plus iota complex number. This is in ordered pair, this is 1 1, and its complex conjugate should lie on the opposite side of the complex plane, that is on this side, and that would be 1 minus iota here. So we can also write it 1 minus 1. So that is easy to understand from your basic concepts, but we can also calculate. Okay, so if lies exactly opposite to this side, then if this is the angle pi over 4, as we have seen, pi over 4, or what you call 45 degrees, so then this angle for this guy down below would be minus pi by 4. So what we do, we just replace from our understanding 1 minus iota equal to square root of 2. So r would be the same, and e to the power minus iota pi over 4. Simple as that. What about the overall complex number? So the overall complex number now becomes easy. So you have square on top, you have 1 plus iota square divided by 1 minus iota, and then 1 plus iota squared is 2 e to the power iota pi half, and down below you have square root of 2 e to the power minus iota pi 4. And if if you simplify this, you get square root of 2 e to the power iota 3 pi over 4. So this is our complex number in polar representation. And how we now represent it on a complex plane. So it would be again simple. So it has square root of 2, meaning that it has x and y equal to 1 1, but we don't know the signs, so signs we will determine from our we just open this up. Okay, so what we do, we write square root of 2 e to the power iota 3 pi over 4 in the form of sine and cosines. So we write square root of 2 cosine of 3 pi over 4 plus iota sine of 3 pi over 4. And we know that square root of 2 and this cos of 3 pi over 4 is minus 1 over square root of 2, and plus iota sine of 3 pi by 4 is 1 over square root of 2 simply. So our net complex number will be minus 1 plus iota. So this is the Cartesian or simple plane representation of iota 3 pi over 4. And this is the same answer that we got previously when we evaluate the thing directly. How would you plot it here on the plane? It would be simple. So you have x equal to 1, x is equal to minus 1. So in the form of ordered pair, I just write it here. So in the form of ordered pair, it is minus 1 1. So we write it on this side. In this second quadrant, we have x minus 1, x in minus and y in plus, x negative and y positive. So and again the angle is 135 degrees, so our number should lie somewhere here, minus 1 1. So if you draw now r, so r will be again square root of 2, and this angle, you will determine the angle from 0 to this, and that is 3 pi over 4 r, which is equal to 3 pi over radian, which is equal to 135 degrees. Simple as that. So this problem was necessary to tell you that a number that is written in somehow complex shape, you can evaluate it and you will get the final thing pretty easily, and you can develop the understanding along with it, that what is happening and what you are actually doing. Moving on, what we are going to learn next is the power and the root of a complex number. So this is rather easy to understand, that whatever power you put on top of a complex number, it just gets absorbed inside the angle. So I write, okay, the extra power gets absorbed inside the angle of a complex number. So you have here, you see on screen that you have z to the power n. You are given a complex number, that is z to the power n, and you know that complex number itself is equal to r e to the power iota theta in the shape of polar coordinates, and then you get r to the power n. So one power comes on r and the other power gets absorbed in the angle of the function. So if you now expand e to the power iota n theta, so e to the power iota n theta is simply cos of theta plus iota sine of theta. So this n, if you now take the power, it looks quite complex. But if you have absorbed this power already, as I have shown here, then this power is simply multiplying the angles, and then it is easy to evaluate. In this shape, it is very difficult to evaluate cos of theta plus iota sine of theta raised to the power n. But if you do this treatment here, then the power just gets absorbed inside the angle, and thus whatever power it is, it becomes really easy to evaluate. So this thing goes directly here. This step is just for the sake of understanding, but we will never remember this. If similarly, if you have now some root of complex numbers, for example, if you have complex number raised to the power 1 over 2 or square root, or 1 over 3 cube root, or 1 over 4 quad root, then again this thing becomes simple, that it gets absorbed inside the angle, and you write simply, if you have z to the power 1 half or 1 n, 1 over n here, just like in this situation, then it gets absorbed, and at the end of the day you get this expression. So from here you go here. So a typical example, a very simple example is given here. So if you have to evaluate, so you are given this kind of thing, that you have to evaluate e to the power iota pi over 10 raised to the power 25, then you simply iota pi over 10, so then you just multiply it inside, and at the end of the day you get very simple expression, that is e to the power iota pi over 10 multiplied by 25, so you get e to the power, or I just write exponential iota that is 5 over 2 pi, and that is equal to exponential of 2 pi plus pi over half iota, write it like this, and you have now in principle e to the power 2 pi iota times e to the power pi half iota, and e to the power 2 pi iota is basically 1, and e to the power pi half iota is iota. So you can check this rather easily. Cos of 2 pi plus iota sine of 2 pi, this thing, and this thing again, including exponential, sorry. So that would be including exponential. So this would be cosine of pi half plus iota sine of pi half, and this thing is 1, and this thing is 0, and this thing is 0, and this thing is 1. Here we are left with 1, and here we are left with iota only. So you get just answer that is equal to iota. So looking complex number is not actually that much tricky or difficult, so we can do it rather simply. So another thing that we usually use in complex numbers is that we use if we have exponential a complex number in the exponential, the complex number itself in the exponential, that is you need to take care. So e to the power z, and z itself is a complex number, so you just replace it with its Cartesian form, e to the x plus iota y, and then you are writing it as e to the power x times e to the power iota y, and e to the power x remains like that, and e to the power iota y you can write as cosine of y plus iota sine of y. Easy as that. So these are some terminologies basically that we use sometimes to evaluate a function that is complex like this, the function that is somehow not so easy to be understood. So as an example, so you are given e to the power 2 minus iota pi, so you just simply do the calculation and you get that, okay, so this complex number is not that complex, so it can be written easily as mentioned. And when we have z replaced by z conjugate, e to the power iota theta is cos theta plus iota sin theta, and e to the power minus iota theta is cos theta minus iota sin theta. But these expressions, although they look simple, but they can be used to express sin theta and cosine theta in terms of complex numbers. So if you now add, so if I call this equation A and I call this equation B, so if you add A and B, you get this equation here. You get cos theta in terms of e to the power iota theta plus e to the power minus iota theta divided by 2. And if you subtract b from a, subtract b from a, then you get this equation, sine of theta. So they are actually easy to remember, and they are very useful at times when we are doing some calculations that are not simple, but if we do this kind of expansion, then they become very easy. And this has an application that even complex numbers themselves, the sines and cosines of complex numbers can also be written as in the form of summation or subtraction of two exponentials. So you should keep in mind that sine of z and cosine of z can be written like these, and these formulas can be used interchangeably. So I think you get what I want to say here. So as an example that is mentioned in the book is, you have to evaluate cos of iota, for example. Cos of iota does not make any sense normally if we don't know these formulas. But if we know, then what we use, okay, I'm referring to this kind of formula here. So you just plug in the values. Cos of iota is e to the power iota times iota and plus e to the power minus iota times iota. One iota from the formula and other iota from this thing here, and then it becomes easy to evaluate. And if you do this calculation, we get some number here instead of cos of iota. Normally cos of iota is difficult to evaluate, but we can simplify this in terms of exponential, and you can add and subtract these exponentials, and you get 1 plus 5. You know what is the value of e. I am pretty sure you know what is e. And also you can do some complex numbers, even more complexer functions by using this formula. And again, the treatment is simple, and at the end of the day you have to simplify certain terms. So e to the power iota pi by 2 is iota, as we have discussed a while ago. And similarly we have e to the power minus iota by 2 is minus iota. So if you simplify this, so this complex number becomes just 5 over 4. So in exam I can ask you questions like these, that tell me what is this kind of a number is, and you have to convert it into a simpler form like this, 5 over 4 or something like that. Okay, so I just zoom it in so that you can see it clearly. Okay. So another thing is, you can write hyperbolic functions in terms of complex numbers also. So if you have exponentials which do not contain any exponentials, then actually you can open sine and cosine which have exponential attached to their angle. So these functions are called hyperbolic functions, and I will not go into details of hyperbolic functions because this is a whole lot of its own category. But as simple as that, you can write sine of iota y as exponentials which do not contain any iota, and also cos of iota y as exponentials which do not contain any iota inside the exponential. So that is easy to remember. These are some formulas that you should always keep in mind whenever you are doing calculations. And we will now proceed to actual stuff. That is our chapter 14. This was our chapter 2. We will stop studying chapter 2. I will explain one smaller thing today, and that would be the end of chapter 2, and then we will move to chapter 14. Next is our chapter 14, that is our actual stuff. I introduced you to complex numbers via chapter 2, although it was not so mandatory in the beginning, I thought, but then I said, okay, you should somehow revise what complex numbers are. So next we will do chapter 14 of the book. I will give you some exercise problems from chapter 2, but they are okay. Our actual stuff lies in the chapter 14. So one more thing that I need to explain today is, so if you are given a complex number or e to the power iota theta, but your actual function is something log of z. Your function is log of z, and you need to evaluate log of z. So what you do, you take log on both sides of this complex polar form. So you write log of z equals log of r e to the power iota theta, and you simplify this as log of r plus log of e to the power iota theta. So you just distribute the log, and this will be log of r plus this would be log and exponential cancel each other, so you get iota theta. So this is usually what we write as using the power rule and using the logarithmic rule, and this is our function. But you cannot define all the time a function with this formula. This formula is incomplete. This formula is incomplete. Reason is, or incomplete, or what you call it, not so sensible, because whenever you add an angle 2 and pi to this theta, the answer does not change, as I told you before. So log of z is, in actual, it is log of r plus e to the power theta. We discussed this in a previous lecture and also in the class discussion. So that is, if you add 2 n pi into this angle, again it remains log of z. So what that means, that now this is a complete description. And what we have written on top here is just one value of this function. So actual function log of z, this thing that we have mentioned here, the actual function is multi-valued, meaning that it has very many values. For each theta, it has infinite number of values for each pair of r theta values. So you fix r and theta, but the function will still have infinite number of values depending upon this n, because you rotate for 2 pi degrees and you get the same value again, and you again rotate and you again rotate and you get the same values. But you cannot take all the values when you are evaluating or you are solving a problem. So you cannot take all the values, infinite number of values of a function. So what you take, you fix n also. So what we evaluate in mathematics, what we evaluate is just one value of n. It can be any n. So it can be n is equal to 0. For example, n is equal to 0, or n is equal to 1 or 2 or 3, whatever. So when you do this, you get this function back. So I mentioned here that log of z, that is equal to log of r plus iota theta, is a branch cut or sub branch, whatever you call it, branch cut or sub branch of actual function, which contains log of r plus iota theta plus 2n pi. So you are always evaluating this kind of a function when you have a log of something. So you are always evaluating some branch of this function, not the whole function. You cannot do that. So that you have to remember always. And that is it. That is it for today's lecture. I hope you have understood some things, and from next lecture onwards we will shift to chapter 14, that we will deal with the functions of complex number, and we will start the actual stuff that is a part of your schema studies. So till then,